Hi, so if you remember the last video about RSA encryption, we mentioned that M was the message, E was chosen to be co-prime to phi n, and hence it has an inverse D, okay, modulo phi n, and hence this will always work, okay. So thing is, why this thing always work like ED, M to the ED is M, why is that so? So let's try to see this thing. Now E is co-prime to phi n, and hence it has an inverse, okay, which is basically same as to saying that there existed D, so that E times D is congruent to 1 mod phi n. Now this basically boils down to existence of some number k, so that phi n k plus 1 is ED. Now if we consider this equation, we want to prove this thing, okay. We want to prove this is our affirmation. So now if we see this thing, m to the ed boils down to m to the phi n k times m, okay. Now m to the phi n is p minus 1 times q minus 1 k, okay. Now if m happens to be, so let us consider two cases. Case 1, if m happens to be co-prime to n, okay, so in that case it is co-prime to p, it is co-prime to q also, because n is pq, and n equal to pq, okay. So in that case, using Fermat-Little theorem, we know that this is nothing but 1 mod p, and using the same theorem, this also holds true, okay. P and Q are co-prime, so m to the, now this is valid, and hence if I raise it to q minus 1, it is valid too, so which is same as to say p minus 1 q minus 1 is equivalent to 1 to the q minus 1, which is again 1. This is nothing but phi n, okay, yeah, and hence this is nothing but m to the phi n is congruent to 1 mod n. Good. Yeah, I'm sorry for these artifacts, okay. M to the phi n is congruent to 1 mod and 1 mod p, sorry, this was all mod p, okay, so 1 mod p, okay. Now in a similar fashion, one can prove that m to the, I don't know what's happening, yeah, so in a similar fashion, one can prove that m to the phi n is congruent to 1 mod q, and hence using these two equations, we can conclude that m to the phi n is nothing but 1 mod n, okay, and hence m to the phi n times k is 1 to the k and now m to the phi n k times n is 1 mod n. This is nothing but m to the phi n k plus 1 and hence ed. So we just prove what we wanted to prove. Now let us consider the second case when m and n are not co-prime. But in that case, since n is a product of two primes p and q, pq, okay, I don't know what's happening. Yeah, sorry for this thing. So since n equal to pq, as we recall, okay, so m not being co-prime to n, this basically boils down to say that p is not co-prime to m or q, which is basically same as to say since p is prime, p is a divisor of m. But if this thing happens, m to the p minus 1, m to the phi n in fact is 0 mod p, and hence this is also the case, okay, and hence m to the, but m is also 0 mod p. In fact, I could have just said, yeah, m to the ed, and hence we are done with p. Now if q does not divide m, q does not divide m, then I don't know what's happening. Yeah, there is some problem with, in fact, q and m are not co-prime. Then in that case we have just proved in the case 1 that m to the ed, okay, which is equal to m to the phi n k plus 1. This is nothing but congruent to m mod q. So this is same as m mod p. M to the ed is same as m mod p, yeah, and m to the ed is same as m mod q, and hence m to the ed is same as m mod pq, and hence we are done even in this case. Yeah, of course, I mean we can have various cases over here in case 2, namely p divides m and q divides m. But if q divides m, then following the same recipe one can prove that m to the ed is m mod q also, and hence this holds true. Yeah, and I mean if p, we can interchange the role of p and q also. So basically what we have proves that m to the ed is m mod n, and hence what we were trying to achieve can be achieved in RSA encryption using this particular law. Thank you.